Welcome to the deep dive. Today we're tackling a massive complex stack of sources. It's essentially the ultimate insider's guide to the deep-end questions you face in advanced software interviews.
It really is.
And this isn't just theory, it's a compilation built by an industry veteran with, what, 15 years in the .NET trenches?
That's right. And our mission today is to, give you a shortcut past just memorization. We're sifting through over 250 highly relevant questions.
That's a lot.
It is. It spans the entire .NET ecosystem, from C# fundamentals and OPS to SQL, MVC, and critical design patterns. We want to expose the subtle yet vital distinctions and the practical why behind all this.
Exactly. We are cutting through the noise to focus on the concepts that truly separate a competent developer from, say, a knowledgeable architect. This is all about foundational comprehension, the kind of understanding you just can't fake.
I agree.
Okay, so let's unpack this, starting with the absolute fundamentals.
Let's begin at the very beginning, clarifying the landscape itself, because this is a basic question that, gets asked surprisingly often, C# versus .NET. Right.
So C# is the object-oriented programming language. It's the specific syntax of the structure you use to write the instructions.
And .NET is the environment that runs it.
Exactly. .NET is the framework and, crucially, the environment that hosts and executes your C# code. This includes the huge library set and, the common language runtime, the CLR.
And the CLR is what handles all the background stuff, like memory management.
Yep, it's managing execution, handling garbage collection, ensuring security. So you write C# code for the environment that .NET provides.
That makes the division of labor really clear. So since C# is object-oriented, let's quickly touch on the benefits of OPS. Beyond just creating software around object, what are the primary commercial advantages?
The sources really confirm the big four benefits. First is code reuse, mainly thanks to inheritance. Second, you have flexibility, which comes from polymorphism.
The ability of one thing to take many forms.
Precisely. Third is security, through encapsulation, which protects your data. And finally, scalability, because everything's modular and just easier to manage. Modularity is key. But you mentioned a drawback. The sources note OPS is not suitable for small applications. Why is that? Why is all that structure suddenly a negative?
Because for a small utility or like a simple script, the overhead of defining classes, interfaces, and maintaining that whole OPS structure, it just introduces complexity without any real benefit.
So you spend more time building the scaffolding than the actual house.
It's total overkill, yeah. You spend more time on the structure than the function.
That's a great piece of practical context. Now let's nail down a crucial distinction that trips people up. Abstraction versus encapsulation. They sound similar.
They do, and that's a challenging question. It really gets to the heart of the difference. Encapsulation is all about data protection.
Okay.
Yes, private fields restrict direct access, but encapsulation, which you usually implement with properties, gives you a controlled gate for reading or writing that data. You can put validation logic right inside the getter or setter.
So you can make sure the data is always valid no matter what.
Exactly. It wraps the data and the methods that operate on it into one secure unit.
Okay, so encapsulation is the practical mechanism, the gatekeeper. What about abstraction?
Abstraction is more philosophical. It's about hiding complexity. You use abstract classes and interfaces to show only the required functionality, hiding all the messy internal details.
So you just show what it does, not how it does it.
Precisely. It reduces the cognitive load for whoever is using your class.
That distinction, data protection versus complexity hiding, is incredibly useful.
Okay, let's pivot to another class-level concept. Preventing inheritance. You've got two main tools in C#, sealed and static. When do you choose one over the other?
Well, this choice really reflects a design decision. If you use the sealed keyword, you're basically saying, this class is finished, no one should extend it.
So you're locking it down.
Right. You prevent other developers from modifying its behavior through inheritance. But, and this is key, you can still create an object of that sealed class.
And static is different. Static is a much stronger commitment. A static class is really just a container for utility functions. The CLR won't even let you create an object instance of it.
So no new keyword.
None. You're saying this functionality is a global resource that never needs its own state? If you need objects in state, you have to use sealed.
That's a critical differentiator. Now, for the listener, here's a thought. If C# consciously avoids traditional multiple inheritance, to get around that diamond problem, how does it let a class get behaviors from multiple sources?
And the answer there is by implementing multiple interfaces. Interfaces are just contracts. They don't have implementation. So a class can promise to fulfill several contracts, getting multiple behaviors without any risk of conflict.
Moving on, let's look at performance and memory. This is where things can get really slow in production if you're not careful. First up, boxing and unboxing. What's the actual cost here?
This hits on the fundamental split between value types and reference types. Value types, like an int, they live on the stack, which is super fast. Reference types, like an object, live on the heap.
And the heap is managed by the garbage collector, so it's slower.
Right. And boxing is moving a value type from the fast stack to the slower heap, converting it to an object. This means allocating new memory on the heap and copying the value.
That sounds expensive if you do it a lot.
It's very expensive. If you do it in a loop, for example, it leads to performance degradation and, even worse, heap fragmentation.
Which makes the GC's job harder, slowing down the whole app. So you only do it when you have to, like with old array lists.
Exactly. And remember, unboxing is the reverse process, which also has overhead because it requires typecasting and runtime checks.
This memory concern leads us right to string manipulation. String versus string builder. If I'm just adding text together, why does the choice matter so much?
It boils down entirely to memory allocation because of immutability. The standard string type is immutable.
Meaning you can't change it.
Right. If you take a string and add something to it, the original string in memory isn't touched. The system allocates a brand new chunk of memory on the heap for the new combined string.
So if I run a loop 1,000 times to build a report, I've just created 1,000 temporary useless string objects for the garbage collector to clean up.
That's the practical consequence. I actually once saw a data logging process that took 10 minutes to run just because it was using string concatenation in a loop.
Wow, 10 minutes.
Yeah, we switched it to string builder, which is mutable, and the time dropped to under 30 seconds. It just uses an internal buffer and reuses that memory. For any kind of frequent text changes, it's non-negotiable.
That anecdote says it all. Now let's tackle the memory management trio. Dispose, finalize, and finally. Let's start with the GC. You mentioned it uses generations.
Why? The generations concept is the GC's main optimization. Most objects you create are very short-lived, right? Like variables in a loop.
Sure.
So the GC divides the heap into generations, lever 1 and 2. It checks generation 0, the youngest objects, way more frequently because they're most likely to be garbage. This avoids expensive scans of the entire heap.
Okay, so the GC handles manage memory. Where do dispose, finalize, and finally fit in? I'll admit I used to confuse dispose and finalize.
That's a common and dangerous confusion. It's about deterministic versus non-deterministic cleanup. Dispose is called explicitly by you, the programmer.
Often in a using block. Right?
Exactly. It gives you deterministic cleanup. You know exactly when your unmanaged resources like file handles or database connections are released.
And finalize is the opposite.
Finalize is non-deterministic. It's a special method called automatically by the GC right before an object is destroyed. The problem is you have no idea when the GC will run, so relying on it is risky.
Because your database connection could be held open for way too long.
Exactly, causing all sorts of problems.
And finally is the outlier here.
Yes. Finally has nothing to do with memory disposal itself. It's purely for exception handling. The code in the finally block always executes, whether an exception happened or not. It's for cleanup, but it doesn't replace dispose.
That is fantastic clarity. Okay, shifting gears. Section 3, database interaction or web architecture. Let's start with a great debate, 8.0.NET versus Entity Framework. Why would I still use raw 8.0.NET today?
Well, Entity Framework, or EF, is pretty much the industry standard. It's an ORM, an object relational mapper that sits on top of 8.0.NET. Its main appeal is just massive developer productivity.
How so?
With EF, you write queries using LINQ. So instead of writing raw SQL, you write C# queries, and EF generates the SQL for you. Plus, it's database independent. It works with SQL Server, Oracle, whatever.
That sounds like a total win, so why would I ever go back to 8.0.NET?
The trade-off, as always, is performance. Because EF is a layer on top of 8.0.NET, there's a small measurable overhead. So when you need absolute raw speed, like for a huge data import, 8.0.NET is slightly faster.
It's the faster but much more difficult path.
That's a perfect way to put it.
Staying with 8.0.NET, let's quickly hit the two data access architectures.
Absolutely. First, you have the connected architecture. This needs an open, constant connection to the database. The data reader is the main tool here. It's super fast, but it's read-only and forward-only.
And the other one is disconnected.
Right. That uses tools like the dataset. You pull down all the data you need, the connection is dropped, and you work with a local copy. You can make updates, then reconnect later to push the changes.
Very useful for apps that might not always be online.
Vital for them, yeah.
Okay, let's move to SQL constraints. Primary key versus unique key. They both make sure data is unique, so what's the fundamental architectural difference?
The difference is how they interact with physical storage. A primary key is the ultimate row identifier. It can't have nulls, and you only get one per table. Crucially, it creates a clustered index.
A clustered index, meaning?
It determines the physical order of the data on the disk. Think of it like sorting the actual pages of a book alphabetically.
So finding things by primary key is incredibly fast.
The fastest. A unique key is a bit different. It can accept one null value, and you can have more than one per table. It creates a non-clustered index.
Which is like the index at the back of the book.
Exactly. It's a separate list that points to where the data is, but it doesn't change the data's physical order.
That makes the storage difference crystal clear. Finally, in architecture, let's compare controllers. Web API versus MVC. What's the main point here?
They serve two totally different masters. An MVC controller's job is to serve a user interface. It provides view support, it processes data, and renders an HTML page for a person to look at.
And the Web API controller is strictly for machine-to-machine communication.
Precisely. It doesn't provide view support. It's designed to expose data endpoints as HTTP services, returning raw data like JSON or XML for, a mobile app or JavaScript front-end to consume.
And there was an important evolution in how they return data, right?
Yes. The shift from manually creating an HTTP response message to using the iHTTP action result interface and now iAction result, this was a huge deal for abstraction. It makes the API endpoints much cleaner and, most importantly, way easier to unit test.
That brings us perfectly to our final section, software design philosophy. Let's tackle the difference between solid principles and design patterns first. Are they the same?
Absolutely not. And this is a key distinction. It's the difference between philosophy and practice, or guidelines and recipes.
Guidelines and recipes, I like that.
Solid principles are abstract guidelines. They're rules for how you should think about designing systems to be flexible, maintainable, and scalable.
And design patterns are the practical application of those guidelines.
Yes, design patterns are concrete, reusable solutions or blueprints for solving common, specific problems. They are the field-tested recipes.
Let's focus on the two foundational solid principles, starting with SRP, the single responsibility principle. Why is it so critical that a class should only have one reason to change?
Well, imagine a class called report generator. Let's say it does three things. It fetches data, it calculates financial totals, and it formats the output as a PDF.
Okay, I see where this is going.
If the financial rules change, you modify the class. If the database schema changes, you modify the same class. If the PDF library changes, again, same class.
It's a three-way coupling disaster.
It violates SRP. By splitting those into three different classes, a change to the database logic only forces you to retest the data fetcher class. It makes testing and deployment so much easier.
And SRP is a prerequisite for the next one, OCP, the open-close principle.
That's the critical connection. OCP says that software should be open for extension but closed for modification. If you follow SRP, your core classes are stable. If you need new functionality, like an Excel report, you extend the system by creating a new Excel formatter class. You don't go back and modify the tested PDF formatter source code.
So OCP is about making the whole system stable and robust over time. Now, looking at design patterns, let's focus on creational patterns. What's the main problem they're solving?
They all deal with how objects get created, and the central problem they fight is tight coupling, which is caused by using the new keyword directly in your code.
Right, because then your code is permanently tied to one specific class.
Exactly. Creational patterns decouple the client code from the concrete classes it needs.
And the most famous example is the singleton pattern.
The singleton ensures a class has only one instance, ever. It's used for things like a central logging service. But to do it right, you have to follow 4 strict steps. Make the class sealed, use a private static instance, have a private constructor, and provide a public static getter method. You miss one step, and it can all fall apart.
The other key one is the factory pattern.
The factory pattern is for when you need to create an object, but you don't know the exact type until runtime. It abstracts the creation process. The client just asks the factory for an object, and the factory figures out which specific one to create and return, hiding all that complexity.
That feels like a complete loop.
Yeah.
We've gone from basic C# types all the way up to these high-level architectural choices.
Exactly. We've covered everything from low-level memory handling, like boxing and string immutability, to high-level architecture, like choosing EF over 80.NET. And the common thread through all of it is understanding the trade-offs.
Right. You're always trading something. Speed for flexibility or simplicity for resilience.
Always.
You are now armed with the kind of foundational knowledge that honestly takes years of hitting brick walls to gather.
Yeah.
What stands out to me is that every technical choice we discuss ultimately comes down to making sound design decisions.
And that leads to a final provocative thought for you to explore. We learned that the DRY, or don't repeat yourself principle, is often enforced through inheritance, but we also champion the solid principle of OCP, which says classes should be closed for modification.
Ah, I see a conflict there.
There can be. So in a large, complex application, how might the goal of code reuse through inheritance sometimes clash with the goal of flexible design required by OCP? And how do modern concepts like dependency injection help resolve that tension? Now that is something to mull over.
That's all for this deep dive. We hope this shortcut helps you on your learning path.